Hey, welcome back. Today we're going to begin talking about some of the properties of trigonometric functions, and we call these the fundamental trigonometric identities. Basically, they're the properties that the trigonometric functions have that help us work with them and manipulate them in order to find certain values of angles and the properties of angles that we're working with. For the sake of the conversation and what we're learning today, the term identity, basically, when we're talking mathematically, it means that it's a statement that two things are equal, that something, no matter what we do to it, is always going to equal something else. For example, the additive identity means that anytime we add 0 to a number, it's always going to equal that number. So it's always telling us that it's going to be the same thing. So likewise, we have trigonometric identities that no matter what angle we put into these things, they're always going to equal out to be a certain value in relation to the other trigonometric functions. So anytime we have a statement between two values that are always going to be equal no matter what, we call that an identity. And when we put a trigonometric function in the mix, we call it a trigonometric identity. So there's lots of problems that you can run into with trigonometric identities, but for right now, we're just going to kind of discuss the fundamental ones, the basic properties that we get from the ideas of the definitions of what these functions are. So the first trig identities that we're going to look at are what we call the reciprocal identities. Now, these are based off of some definitions that we should at least be pretty familiar with. For example, we know that the sine of a function and the cosecant of a function are reciprocals of one another. Sine and cosecant, kind of like if you flip over the value of the sine, you're going to get the cosecant. So this idea kind of based off of that. The sine of theta is equal to 1 over the cosecant of theta. Basically saying that cosecant and sine are reciprocals of one another. Likewise, we have cosine of theta is equal to 1 over secant of theta. It's pretty much the same concept. One is the reciprocal of the other. Tangent of theta is equal to 1 over cotangent of theta because, again, they're reciprocals. And we can kind of look at this in the other way as well. If sine is equal to 1 over cosecant is equal to 1 over sine. Secant is equal to 1 over cosine, and cotangent is equal to 1 over tangent. Again, these are all based on the reciprocal of each trigonometric function. We've learned these definitions already. We learned that cosecant was basically the reciprocal of the sine function. And that's all we're looking at with this definition here. But we're just kind of laying these out in rules that we kind of are saying that this is just the way it is, and we know this is going to be something we can use from now on anytime we need to deal with it. Likewise, we have what we call the quotient identities. Now, when we think about these, the quotient identities, we learned when we were talking about the unit circle that tangent was equal to y over x, whatever the y coordinate was over the x coordinate. But at the same time, we also learned that sine was equal to the y coordinate. And we learned that cosine was equal to the x coordinate. So, it just kind of flows that if we're going to say tangent is equal to y over x and y is sine and cosine is x, then tangent must be equal to the sine of theta divided by the cosine of theta. And we can do the same thing with cotangent, because cotangent is just tangent inverted, flipped over. So if we take cotangent, it's going to be equal to cosine over sine. And again, these things are just kind of based off of quotients of the sine and cosine functions. So when we say quotient, again, we're meaning dividing. So we're dividing sine divided by cosine, or we're dividing cosine divided by sine. The reason why we're doing this is when we work with multiple functions together. A lot of times we might have a bunch of different ideas going on, and we want to convert them all to be in the form of sines and cosines. So if we can take a tangent and break it down into sines and cosines, that works to our advantage. And we'll look at that in a few moments. I'm kind of getting ahead of myself a little bit, but I just want you to see the reason why we're doing this. We want to kind of convert things to sines and cosines. The next thing we're going to look at is the Pythagorean identities. But before we do that, I kind of want to just explain what the Pythagorean identities are based off of. You'll remember when we learned the unit circle, and I'm trying to move this around a little bit. Hold on. When we learned the unit circle, we learned that the x-coordinate of our angles, for instance, we might have an angle here, and the x-coordinate that was formed from that in the unit circle was our cosine value. And I'm trying to write here with the cursor. So our x is always equal to our cosine, and the y was always equal to our sine. Now, we learned that, and we were dealing in the unit circle, and the hypotenuse was always equal to 1. So we have this kind of setup going on here. X was our cosine value, and sine was our y value. Our y value was sine. So based on that and some other things that we've learned, it kind of flows through the Pythagorean theorem that that this side squared, which we call sine squared, and cosine squared, which would be that other side, are going to be equal to 1 squared. Well, what's 1 squared? It's 1. So we have this idea that's a very important concept for us that we're going to use a lot, called the Pythagorean identity. And it's that sine square of an angle plus cosine square of an angle is equal to 1. And we call that the Pythagorean identity. And it's a very important rule that we can apply through a lot of ideas, and we can use it to relate a lot of concepts that we have in dealing with the the trigonometric functions. So Pythagorean identities are all based on this concept of the Pythagorean theorem. And that's why they got their name, and it's that sine squared plus cosine squared is equal to 1. In other words, the y-coordinate squared plus the x-coordinate squared is going to equal to the radius squared. And the radius in the unit circle is always 1. So taking that concept of the unit circle and applying the Pythagorean theorem, we get this concept that sine squared plus cosine squared equals 1. Now, we can adjust that based on what we know about the reciprocal identities and the quotient identities. Say, for instance, we were to take the entire sine squared plus cosine squared equals 1, and we were to divide them all by cosine squared. Well, if we did that, we would have this to start off with, but then we divide everything by cosine squared. Well, then we would be able to relate the quotient and reciprocal identities that we just talked about. Sine squared over cosine squared would be equal to tangent squared. Cosine squared over cosine squared is of course going to be 1. And 1 over cosine squared, based on the reciprocal identities that we just talked about, is going to be secant squared. So we have another version of the Pythagorean identity, and that is that tangent squared theta plus 1 is equal to secant squared. We can do the same thing by taking that sine squared cosine squared equals 1, or sine squared plus cosine squared equals 1, and dividing everything by sine squared instead of cosine squared. Well, what happens when we divide sine squared by sine squared? We're going to get 1. And then we have cosine squared divided by sine squared, which we should know by now is going to be cotangent based on the quotient identities we just talked about. And 1 divided by sine squared is going to be cosecant squared, as is given to us by the reciprocal identities. So we have the Pythagorean identities, and it comes in 3 general forms. Sine squared theta plus cosine squared theta equals 1. And then we just kind of rewrite that same statement by saying tangent squared theta plus 1 is equal to secant squared theta. And then 1 plus cotangent squared theta is equal to cosecant squared theta. So these are the 3 basic, or 3 of the fundamental theorems that we need to know, called the Pythagorean identities. And if you were to look up anything about trigonometric identities, this would be the one main concept that you would learn. So let's look at some examples here. Let's say we've got the fact that we know that cosine of theta is 3/4, and we want to find secant of theta. Well, we should think about how we know that cosine and secant of theta relate to one another. And if we think a little bit, you should probably realize that these are reciprocals of one another. So if we know cosine, we can apply the reciprocal identity to find secant. And what we'll do is we'll just take that cosine and flip it over, or we'll put 1 over 3/4, which would tell us to say 1 times 4 over 3, which would be 4/3. And we would learn that the secant of theta is 4/3. Another way of looking at this would be to take a problem like this and say cosine of theta is 3/5, and we want to find cosecant of theta. Well, they don't relate directly through the reciprocal identities. We know that cosecant kind of relates to sine, but if we have cosine, we can find sine based on the Pythagorean identities. So what we would do is we would take cosine squared plus sine squared, or sine squared plus cosine squared. And in this case, cosine squared is 3/5 squared, and that's equal to 1. Well, 3/5 squared is 9/25. 1 can be written as 25/25. So when we subtract over, we get that sine squared of theta is equal to 16/25. Well, we can get rid of the square. Hopefully you know that by taking the square root of both sides, and we find that sine is going to be either positive or negative square root of 16 over square root of 25, which would be 4/5. So we can take one piece of information and find other pieces of information just based on that concept and using the identities. But if we know that sine is 4/5, and we know that cosecant is the reciprocal of that, we would just flip it over and say cosecant of theta is equal to 5/4, positive or negative. Now, sometimes we might have an expression like this, as we see in this next example, that we want to simplify. And this, believe it or not, this expression simplifies down quite a bit. The first thing we're going to want to do when we get an expression like this is we want to break it down into terms of sines and cosines. So what we're going to do is we're going to take this cosecant squared and think about how can I get this in terms of a sine or a cosine. So what I'll do is I'll convert it to be cosecant is 1 over sine based on the reciprocal identities. Cosine is already in terms of cosines and sines. So then I'll go to cotangent. Now, if I want to put cotangent in terms of sines and cosines, I'll go back to my quotient identities that we talked about earlier on. And the cotangent function was equal to cosine over sine. So now we have 1 over sine minus cosine times cosine over sine. So now we're just going to go with things. You can multiply first, you would multiply these two items before you would subtract because of our order of operations rules. So we'll say cosine times cosine. That's going to give us cosine squared. And look, we have common denominators. So we'll combine those to one fraction and say that's 1 minus cosine squared over sine. Well, if we go back and we were to look, excuse me, I'm going back a little bit too far, but if we were to look at this function and rearrange that so that it said 1 minus cosine squared, you would find that that would be equal to sine squared. And that's just using a little algebra there. But we have that 1 minus cosine squared is equal to sine squared. So I have sine squared x over sine of x. We use the fact that I have sine squared over sine to the first. We divide that out. That leaves me with sine of x. And that would be a simplified version of all this that we saw up here at the beginning. So, again, just kind of reiterating what I just said. When we're asked to simplify an expression like this, you kind of want to just use these ideas that we just talked about with the identities and kind of convert everything into terms of sines and cosines. And once we do that, you should find some things are going to cancel out, some things are going to combine, some things are going to become this, and we can find something that's going to simplify out. And in this case, we simplified out to be sine of x. Okay, so I have some practice problems here. And rather than pulling them up in the PowerPoint, what I'm going to do is I'm going to look at them with you in Cami, and we'll kind of just sketch through them together. So number one says sine of theta is equal to negative 1/5, and we want to find cosine of theta, but we are in, and this is an important piece here, we are in quadrant 3. Now, we should know that quadrant 3 is over in this area here. And what's happening there is both the x and the y coordinates are negative. So we should know if sine's negative, we also know that cosine is going to be negative. And that's going to come into play in a few minutes. But let's talk about what we're going to do with this in order to get here. We know that sine and cosine are related through this one thing that we just talked about called the Pythagorean identity. So we have that. So we're going to take sine squared, which would be negative 1/5 squared, plus cosine squared, and that's equal to 1. Well, 1/5 squared is 1 over 25, plus cosine squared is equal to, I'm going to take 1 and I'm going to convert it to 25 over 25. And the reason why is because I wanted to get a common denominator here so that I could combine those fractions. So what I'm going to get is that cosine squared is equal to 25 25ths minus 1 25th would be 24 25ths. Now, based on our rules that we've learned, we would take the square root of both sides, and that would leave me with cosine of theta is equal to positive or negative. Well, the square root of 24, we can break that into the square root of 4 and square root of 6. Hopefully you're okay with that. So that would be 2 square root of 6 over 5. And that would be my answer. Now, I do need to go back to this concept. It actually should be positive or negative. And I need to go back to this concept that I'm in quadrant 3. So that would tell me more specifically that the cosine of theta would be negative 2 square root of 6 over 5. So this is actually my answer. I guess I should kind of take that circle off. But again, we're using the Pythagorean identity to relate sine and cosine, and we were bringing in the fact that we knew that we were in quadrant 3, and that meant that my cosine was going to be negative and my sine was going to be negative because both x and y coordinates are negative in that quadrant. And we'll see some problems like that where we're trying to identify what quadrant we're in as to what the sign on this value is going to be. All right, so let's look at number 2. Number 2 says tangent of theta is negative 4/7. We're in quadrant 4. So if we go to quadrant 4, that means that it's over here. And we have a positive x and we have a negative y. So how is that going to play into this? Well, you have y over x here is negative, so that makes sense. But we're trying to find this value here for secant. Now, you'll remember that we learned that, 1 plus tangent squared is equal to secant squared. So, what we have is, and I think I wrote, it's actually tangent squared plus 1 is the way I wrote it in the PowerPoint, but it's the same thing. So we take this, and that's going to be 1 plus 4/7, negative 4/7 squared is equal to secant squared. And we go with that. That's going to be 49 over 49. And you might be thinking, why did I do that? But I'm trying to get a common denominator here. So that's going to be 16/49. Excuse me. Is equal to secant square theta. And I know I'm kind of writing it sloppy, but we have 49/49, which is 1. And we have negative 4/7 squared would be 16/49. Remember, that's going to be positive when we square a negative number. And we have 49 plus 16 over 49. So that would be, 65/49 is equal to secant squared. And then we take the square root of both sides. So what I have is the square root of 65 over 7 is equal to secant squared. Or, excuse me, secant. Now, when we look at secant, secant is based off of the reciprocal of cosine. So it's going to use the x coordinate, it's 1 over x. So our x coordinate was positive. So we'll have a positive square root of 65 over 7 for our value for secant. Okay, so hopefully that's making some sense to you. Let's go ahead and look at the last couple of problems here where we are simplifying these expressions. Now, if you'll remember, I kind of spoke to you earlier about this, and we said when we are simplifying an expression, we want to get it in terms of sines and cosines. So what I'm going to do is I'm going to take each of these terms and I'm going to write them in terms of sines and cosines. Cosecant, for example, is equal to 1 over sine of theta. And then we're going to take cotangent, and cotangent is equal to cosine of theta over sine of theta. And that's the reciprocal, or excuse me, not the reciprocal, the quotient identities. Now, based on our rules, what you do in this point is you take your bottom and you flip it over and you take it to the top and multiply it. So what I have is 1 over sine of theta, and I'm going to multiply that times sine of theta over cosine of theta. Now, if you remember your rules for multiplying fractions, what you have here is sine of theta over sine of theta cosine of theta. And that's just going across the bottom and across the top. But what happens here is the sine of thetas cancel out. So we're left with 1 on top over cosine of theta. Well, hopefully you remember your reciprocals, because that is actually 1 over cosine is equal to secant of theta. So if we were going to fully simplify this, we would call this secant of theta. All right, so I know that's pretty involved, but again, just kind of recapping, we're going to get everything in terms of sines and cosines, and then we cancel out the parts that'll cancel out, we multiply what we can together, and we go with it and simplify. So let's take a look at this last one, and hopefully we can apply these concepts a little further and see what's going on. First off, cosine of x is already in terms of cosine. So like I said, we want to write things in terms of sines and cosines. Cosecant of x, that is going to be equal to 1 over sine of x. And then tangent of x is equal to sine of x over cosine of x. And again, those are things that we learned earlier. So to multiply these things together, you can probably see some things are going to happen, but we're just going to multiply across the top and across the bottom. So what we get is sine of x cosine of x over sine of x cosine of x. And we can see that both of those are going to cancel out. So my final answer here is 1. And that's what that all simplifies to be. So again, if we kind of went through these problems in the PowerPoint, I've just kind of worked through them. You have that if the sine of theta was negative 1/5 and we were in quadrant 3, cosine is what we were looking for. You have these other ones as well. The answers for number 1 were negative 2 square root of 6. That was the square root of negative square root of 24 over 5. Number 2 was square root of 65 over 7. Number 3 simplified out to be the secant of theta. And number 4 simplified out to be 1. So with all that said, I know there's a lot going on there. Basically, you have 3 rules of the Pythagorean identity that you need to make sure you're familiar with. That is sine squared of theta plus cosine squared of theta equals 1. That's tangent squared of theta plus 1 equals secant of theta. And then that is 1 plus cotangent of theta is equal to cosecant of theta. So you want those ideas, and then you want your reciprocal and your quotient identities as well. Hopefully you can apply these things and work with them in your assignments. So if you're having questions, make sure you're asking them in class. If you need anything, please feel free to email me or contact me through Zoom meetings or whatever, and we can sit down and talk about whatever you need to. I look forward to hearing from you. Have a good day.